I'd like to talk about an example where I'm doing discrete convolution and I'm also doing impulse response, or in this case, step response for my convolution. And I'm also going to look at the Z transform and the frequency response and put them all together so you can see them all at the same place. Now, starting again, we're starting with this being my discrete time FIR system. 3 stages. And I see the 3 different stages there. I know that I have an impulse response h of n with 3 delta functions. Again, we're dealing with discrete time space, so we can put this together. Now, a couple of questions I might ask. 1, what happens if I were to look at a step input? This is now a u of n type of thing where it's going to be 0 up until n equals 0 and then becomes all 1 afterwards. You can see the plot here that you would get and generate out of MATLAB for something like this. And then what do you get? Well, what you would do for this approach, you should say, well, let me look at this for delta of n, which is the first one, and then the next delayed one, the next delayed one, the next delayed one. Notice I've got all of these delayed all the way through. Great. Well, and then I would say 1, 2, and 1. Well, the next one's delayed out by another one. And so then I just need to simply add. Well, I get 1, 3, 4, 4, 4, all the way out. In fact, if you look at the plot of it, it's 1, 3, 4, and 4 all the way out. In fact, if you do convolution in MATLAB, you'll see exactly the same response. Cool, this works really well. And in fact, you can talk about this as being 4u of n minus 3 minus 1, because you have a 0, then 1, then 3, then that. That's the minus 3 off the 4, that's the minus 1. And so you think, this is great. I definitely can get the convolution, but let's look at this a little bit clearer. So I can also then do a Z transform of the h of n. And that's a 1, 2, z minus 1, and z to the minus 2. Okay? And that gives me then 1 plus z to the minus 1 squared. And you think, great, we've got all this in really good shape. Now, the next thing that you see out of this is then you go, well, wait a minute, I actually got zeros. In fact, I've got 2 zeros. At e to the j omega hat equal minus 1. Well, and that's equivalent to z to the minus 1 is minus 1. You're like, great, I got 2 zeros right there. Well, I can solve this because this basically then is omega hat equal to pi or minus pi. I imagine I would see that in the frequency response. Well, let's look at the frequency response. And there's a couple ways I could do that. I could see I've got the coefficients 1, 2, and 1. And I know that there's sort of a formula for dealing with FIRs directly. The second thing I could do is say, well, I actually know that z to the minus 1 is e to the minus j omega hat. I already kind of used it a moment ago. And I use that and I put that into the system. And what I find is I get e to the j omega hat, or I get this sort of squared. I pull on one of these out, and I get this interesting thing, right, of these 2 terms. And then I get that squared. And so as a result, well, that's a cosine. In fact, I get 2 cosine for this, and there's a result that gives me 4 out, cosine squared omega hat over 2. That gives me an interesting frequency response where it basically goes to 4 at 0 and then goes to 0 over at pi and minus pi. No surprise, we said the zeros were at pi and minus pi. And so this gives us a case where the low frequency sort of things come through, high frequency things drop off, and I get sort of an interesting shape. Now, if you remember this from what it might have been for just cosine squared, so without the squared term, but just the straight linear term, that gets interesting because that would now have a much more wider bow to it. This has a little more sort of sharper shape. And you start to notice that as you start getting more and more and more sort of powers, things get steeper, this is an interesting sort of observation. Might be helpful depending on what kind of responses you're trying to make.